Gaussian Q function, as it can be equivalently said. This is work that I did quite a long time ago, and it's quite interesting and simple work that is useful. Recently, some people have discovered this work and started using it actually, which motivates me to come back to it and give a little talk about it. All right, so let's get started. And the motivation, of course, is coming from a wireless communications perspective, is that the bounds, or better saying, the error function or the Gaussian Q function, are very useful in computing the error probabilities in communication systems. So to illustrate what we are talking about here, consider a simple digital um, modulation scheme such as the one illustrated here, like a 4 PSK or 4 quant. And so what actually happens is that if you transmit one of these symbols, you eventually receive something that is not quite what you transmitted due to noise and distortions of the channel and whatnot. So you transmit another symbol, and again, you get something else. And you transmit another symbol and something else. If you look at this process over multiple transmission times, what actually takes place is that every transmitted signal that you send is received away from the actually transmitted point. So you get these clouds of received signals around the actually transmitted point. Here we obviously assuming that you already have done some compensation for the rotation that the channel performs, and therefore all we are seeing here is the envelope fading or the noise affecting your system. So now, if we consider that the channel coherence time is sufficiently large, so you have compensated for the channel effect, and at the end of the day, all you're left with is the effect of noise, then those clouds of points around your transmitted symbol constellation points are described by Gaussian probability function or Gaussian density function. So that means that if you go and look into the error events, in particular the so-called pairwise error probabilities that describes the likelihood that you receive a symbol erroneously, then these are described by these so-called tail probabilities. So on the right-hand side here, I have an illustration. Let's say that you transmitted the symbol Si, and you were affected by a certain Gaussian with a given variance, then your the likelihood that you receive a symbol S sub j instead of the transmitted S sub I is essentially governed by the so-called Euclidean distance between the S sub I and the S sub j, and the corresponding noise um, error variance, or the noise variance here represented by sigma square, in that way, right? So you have a Gaussian distribution over one symbol, and you have another Gaussian distribution, another symbol over another symbol. So there is a threshold determined by the Neyman-Pearson theorem that is the point of decision. So any signal that is received below the dashed line here will be detected as S sub j, or any signal that is received to the right of that will be detected as the S sub I correctly. So your probability of error is determined by the integral of the Gaussian function from minus infinity to this midpoint, which in this case is obviously the Euclidean distance dij divided by 2. So in general terms, we can therefore say that these pairwise error probabilities are Gaussian Q functions of ratios between the pairwise Euclidean distance between the points in the constellation and the a function of the noise, where the Gaussian Q function is in fact nothing but a rewrite of the error function, and this ratio here is directly related to the signal to noise ratio. Okay, so again, the Gaussian Q function is just another way for you to write the error function. So from here on, when we start talking about bounding the Gaussian Q function, we are also simultaneously talking about bounding the error function. And of course, by complement, we can also bound the complement error Q function. Now, again, why this is relevant, of course, the pairwise error probability in itself is not the whole story, but the fact is that the symbol and the bit error probabilities of digital modulation systems are determined from such pairwise error probability. So in the case of BPSK, for example, it is well known that the bit error probability is given by the Q of square root of 2 times the SNR. This is, by the way, the same as the bit error probability of QPSK that we just illustrated above. But if you're interested instead on the symbol error probability of QPSK, then this is actually a nonlinear function of the Gaussian Q function itself, in particular, 2 times the Q of root of the SNR minus the square of Q of the root of the SNR. And I mentioned this only to stress the fact that we are going to be focusing on the bound of Gaussian Q function, but we'll also show in the end that you can use the result to obtain also very clean bounds of powers of the Gaussian Q function. So the challenge here is that obviously, as illustrated above, the Gaussian Q function or the error function do not have a closed form. Right? So normally you have to compute them numerically, which, using modern computers is not really a problem for you to visualize, but this can be a significant issue when you are obtaining results that are functions of the Q function. And so you usually would like to simplify them to try to get a nice clean expression. Otherwise, you can easily fall into a situation where everything escalates into non-tractable expressions. Okay, so the story of bounding, of course, is not new. There are many people who consider that, and one of perhaps of the most significant and earliest bounds that one can mention is the Chebyshev bound. Chebyshev bound was invented by Pafnuty Chebyshev. Here is a picture of the man. And the idea is very simple. The bound is super elegant. So what he was trying to do is to find a bound for any generic, for the tail integral of any generic distribution in terms of the threshold and the variance. So the bound is described by this expression here. And if you, second, I don't know what's going on. Okay. If you apply the Chebyshev bound onto the Gaussian Q function or the error function, you can easily show that the one very simple bound that you obtain would be this one, yeah? That the Q of x is upper bounded by 1 divided by 2x squared. Now, if you go ahead and you, so this is a very simple and algebraic upper bound, and if you go ahead and you plot it, you find that it's pretty good for a relatively small range or narrow range of values, but unfortunately it's not that tight, very loose in fact, in the vicinity of the origin. And also another problem is it doesn't have the general shape, the overall waterfall shape that characterizes error probabilities in communication systems, and therefore, although the bound has some use, it's not quite what we are happy with. So another interesting bound that one can consider is the Chernoff bound. That was discovered by Professor Hermann Chernoff from Harvard University. And what he's essentially suggesting is that you can obtain now a bound, and interestingly, in comparison to differently from the Chebyshev bound, this is a single-sided tail integral bound. Yeah? The other one was a bound on both of sides of, integral on both sides of the distribution simultaneously. But here, the Chernoff bound allows you to obtain one that is single-sided, and this is described this way, right? So the tail integral is upper bounded by an exponential function multiplied by the moment generating function of your distribution, and it can be made optimally tight by computing this parameter alpha, which you can either do by first computing this expression and then finding the alpha that minimizes the expression overall, or you can just follow this recipe that Chernoff derived, which the solution of this equation directly gives you the optimal alpha. So once again, if you go and you apply the Chernoff bound to the error function, the Gaussian Q function, you can now obtain a very simple exponential upper bound for it. And if you go ahead and you plot it and compare it against the actual numerically evaluated exact expression, you find that it is not as tight as the Chebyshev bound in a certain region. Beyond that region, on the other hand, and so beyond this point here and before that point, it is. But more interestingly, it actually has the overall waterfall behavior that one would like to see. So in many respects, this can be considered as an improvement of the Chebyshev bound. Now, these bounds essentially remained the most popular for many, many decades until in 1991, someone quite elusive. I tried to find a picture of this person, but I couldn't. And he only has a couple of papers available in the IEEE Explorer. But anyway, very interesting, simple, and brilliant work. John Craig discovered that you can express the Gaussian Q function in this alternative way here on the right-hand side of this equation, in which the variable is no longer in the as a limit of the integration, but actually it's just a variable inside the integrand, while the integration is actually performed over another variable. So this is very nice because suddenly you don't need to do anymore an integration, even numerically, over an infinite range, but rather a finite range. And your the variable of the q is actually just a parameter of that integrand function. So now, uh, after that, it was discovered that somebody realized, that Simon in particular realized, that you could look into this sine square that appears into the integrand here, and realize that in this range of integration, a sine is actually upper bounded by the number one. So if you simply use this into this expression, you can find easily an upper bound for the q of x by integration of this function, which is no longer a function of theta, such that the result is immediately obtained as the exponential of minus x squared divided by 2. All of it divided by 2. So essentially, you improve the previous exponential bound obtained via Chernoff by a factor of 2. Yeah, so this was discovered by Simon and Dusserline in 1998. Now, if we go ahead and you plot that improved Chernoff bound, so to say, or maybe you could call it a Simon bound, against the others that we just saw, you now find that it again has a very nice waterfall behavior, but it's now tighter than the Chebyshev bound over a much wider range of values. Then a colleague of ours, Marco Chiani from the University of Bologna, thought of using the same method more than once. So he said, well, wait a second, I can split this integration from in the region from 0 to pi divided by 2 into 2. And say, okay, if I integrate first from 0 to pi divided by 4, and then pi divided by 4 to pi divided by 2, then the same sign that we had before can be upper bounded respectively by half and by 1. And if you do that, you obtain now a composite two-term exponential bound. And you can keep doing this. You can do it with 3 terms, 4 terms, as many terms as you'd like. So essentially what you obtained was a simple multi-term exponential upper bound, which if you now go and plot in comparison to the previously improved Chernoff bound, I am now no longer showing the original Chernoff and the Chebyshev. You can see that with 2 terms, you get this blue line. With 3 terms, you get this green line, which are, again, tighter than the improved Chernoff bound, quite significant. The end, once more, keeps the same general waterfall behavior that we like to see. Now, sadly, the problem is, as you can already see here in this short illustration, that if you add more terms, you can't really get significant improvement of over the two-term one. All right, so here's where we come in with a new idea. What I thought was, well, can we obtain a two-term exponential bound by simply affecting one of the coefficients and having here an algebraic coefficient? So you have a mixed algebraic exponential bound with only 2 terms, and my idea was, can we optimize the values of a and b such that you have much nicer and tighter bounds? And this is what we're going to show you to be in fact the case. So we obtain ultimately super tight bounds with only 2 terms. Now, another nice, very sort of bonus that we obtain from the work is that we can obtain not only upper bounds but also lower bounds in a single expression with the same shape by only using different values for A and B respectively. So here are the bounds in a nutshell. We are going to go through now and show you how you obtain these results. But as you can see from here, from this, the structure or the shape of the function is the same. Only the coefficients are a equal to 50 and a equal to 2 for the upper bound, or a equal to 12 and a equal to square root of 2 pi for the lower bound, respectively. We'll see later that these values don't have to be exactly those. There are any number of different values that you could use, but these are just two simple rounded values that you can use, and which already gives you very, very nice performing bounds. Okay, so in a nutshell, just before we go into the mathematics, let me show you already, let me catch your attention by showing you how these bounds compare against the exact expression. You can see here now the three-term Chiani bound and our super tight two-term bounds. As you can see here, the blue line, there is a black line here. The black line, you can see that is pretty much overlapping with the black line. So the upper bound is extremely tight. But also the lower bound is already much, much tighter than any other bounds that you have out there. And needless to say, none of the previously mentioned work addressed a lower bounding either. Okay, so let's do a proof by stating what is the basic idea. The basic idea is, okay, start by defining this function. And now we can define the following two differences, right? If you are interested in an upper bound, you can take this function minus the q of x. If you're interested in a lower bound, you can take the q of x minus this function. And you want to find the parameters a sub u and b sub u for the upper bounding case, or a sub l and b sub l for the lower bounding case, respectively. Now, what is the idea here? The idea is, first of all, that if you are upper bounding, you want to make sure that your delta q sub u is larger than 0 for x equal to 0, right? You want to make sure that your upper bound is above the q. Yeah? And likewise, if you are looking for a lower bound at x equal to 0, you want your lower bound to, when subtracted to q, still give you a positive number, right? So the q of x minus the lower bound must be positive also at x equal to 0. So just substituting x equal to 0 into the previous expression immediately gives you the following relationship, which I consider the first condition for upper and lower bounding respectively. So 1 divided by AU plus 1 divided by BU must be larger than half for upper bounding and must be less than half for lower bounding. Now, another constraint that you have is, so this is upper bound is above QX, and the other condition here ensures that the lower bound is below the QX at x equal to 0. Now, the other condition is that beyond this point, if you're upper bounding, if you start from above, you want to make sure that you decay less fast than the Q of x itself. And so if you start from above and your decay is lower, then you cannot go below. And vice versa, if you start from below and you decay faster, then you also cannot go above. That is the basic idea. All right, so for hereafter, I'm going to focus only on the upper bound case because the proof for the lower bound is pretty much the same. It's just, it follows the same steps. All right, so what we want to do is to now inspect beyond the second condition that says that the derivative of this delta q function must be above 0 for all values of x above 0. So now let's write the value of the delta QU explicitly. Remember, this is the shape of the bound generally, right? And this minus the shape of the Q of X is what the delta U is. Now, what I'm going to do is to take an inspiration from Richard Feynman's very famous method of solving integrals by differentiating under the integral sign. It's not quite the same thing, but it's inspired by the same idea. So what we do here is that if I take the derivative of this term on the left-hand side and I integrate it at the same time, I didn't change anything, right? So again, this is the term. I'm taking the derivative of it with respect to x, and then I'm integrating it with respect to s, and this must be, of course, the same result. Now, what is interesting to notice, however, is that because this function has these exponential terms, if we replace the antiderivative with actual determined integrals, we are going to be able to put into the same expression the integral on the right hand side, which is the Q function itself. So going step by step, first let's take the derivative. Yeah, this is just us doing the algebra and taking the derivative. Now I collect the terms. And then finally, again, I use the fact that since both of these terms here decay to zero, I can introduce the limits of integration, because this essentially will be this evaluated at x minus this evaluated at infinity, which is zero, right? So there's no change from here to here. Obviously, in so doing, I have to also introduce, oh, there is a little mistake here. This x should have been an r, right? So obviously, I'm integrating on r until x. Apologies, this x here should be read as r. But now, all I have to do is, if I flip the order of integration, instead of minus infinity to zero, I integrate from x to infinity, then we have to negate the terms, right? So these negatives here become positive. And then I incorporate, as mentioned before, the term coming from the Q function itself into the same integral, obtaining now this combined expression. So now again, remember, what we want is that the derivative of this is larger than zero. And now it becomes very easy for us to do, because we can just take the derivative of this integrand um, and make sure that it is larger than zero. Yeah, so when we do that, the exponential term that is outside has no role whatsoever. All that we need is actually that this term here is above zero. So when we put together these now worked second condition and the first condition, what we obtain is a feasibility region that is essentially a non-convex volume, right? So any point inside this non-convex volume would yield a bound for you. So we can take a look at this solid, yeah? So if this here is the direction of the variable x, this here is the direction of the parameter AU, and this here is the direction of the parameter BU, then we can move a little bit the feasibility region so that you have an idea of how it looks like. Yeah. Let this video run. Okay, it's a pretty nasty non-convex solid. But if you take slices of this solid for different values of AU, then you can see pretty much, you can, by looking at this and this together, you can see that pretty much at each slice in this direction gives you a different two-dimensional feasibility region, and which again, any point inside any of these regions would satisfy the bound. Now, I didn't do it in detail, but if you do the same processes for the lower bound, you're going to find a similar non-convex solid, which you need now to slice to find the values of AL and BL, respectively. Now, it turns out, quite obviously, that all of these flat, so again, as I said, any pair, let's focus on the left-hand side, the upper bound, right? So any pair of AU and BU in the region suffices. But what is also interesting to observe is that obviously all the flat portions are determined only by the C1, because the C1 is the only condition that doesn't depend on X, right? So this is valid for all X. And the curvy, the more difficult ones is what you get as a result of CU and C1. So the idea here now just to find a good value of pair of coefficients is simply to define this function here that describes the non-flat portion of the boundary. Take the derivative and equate to zero, so you find the points, the inflection points of inflexibility, inflection points here, right? So, and you want to stay below that point, right? So for any value of AU that you pick. Now, when you do that, it turns out that you obtain a very simple expression that bounds the upper value of AU And now if when you use this together with the first condition, you can also easily find limiting point on X that makes sure that your surface is convex in a given region outside or within the flat areas. And this gives you immediately, very simply, very using just fundamental algebra, the upper values of the AU and the BU respectively. Once again, if you do now for the lower bound, you're going to have lower values of AU and BU, AL and PL respectively. And that's pretty much it. So this value here, as I said, is actually 52 dot something something something, and this also is 2 dot something something something. I'm just rounding it to clean numbers, and then I put here 50 and 2, and for the lower bound, 12. And it turned out that the BL is not as clean, so I found that square root of 2 pi is sufficiently good number. And for you purists who are thinking, oh, but this is not the optimal, the tightest value, well, again, I bring you to the result. And this is what we obtain with the numbers that I just showed you. On the left-hand side, I have a comparison of the super tight bounds against the Chiari bounds with two terms, and also a comparison against another work that I had done before, in which we use the Jensen inequality to compute much tighter bounds than but using the same idea of slicing the Craig integral in different segments. So those are here given by the white little balls, right? So you can see that they already are much tighter than the candy bounds. But even then, if you see in the inlay figure here, the super tight bounds, however simple, they are much better than in the others. In fact, if you look down on the right-hand side, another way for you to see how tight the bounds are is to throw in Kullback-Leibler divergence and compare them against the actual Q function itself. And what you can find is that the tight bounds, this is so-called super tight bounds, are as tight as a multi-term exponential bound with 100 terms. And I mean, look, if you are doing that exponential bound is 100 terms, you are essentially solving the numerical integration in a very clever way. So it's very difficult for you to outperform this altogether. And now my last word about this is to point out the fact that if you now use these bounds in conjunction with a multinomial theorem, you can also find very nice up and lower tight, very tight bounds on the powers of the Q of n that are all obtained in terms of these series of algebraic terms and exponential. And with that, I thank you for your attention and refer you to these articles here if you want to see any more details. And if you have any questions, go ahead.
I have one. So I wanted to ask you if you already did or somebody else did to generalize these bounds for the multidimensional case. I don't know if it is very trivial to do it or it might require more analysis.
Okay, I didn't do it. I know that they work on this bounding of derivatives. So derivatives not in the calculus sense, but derivations of Q functions did continue. I did some work on all the types of Q functions, the Markov Q function, and so on. There are other types, but not exactly on multidimensional. But I would not be surprised if other people did work on bounds of multidimensional versions of a Q function. I don't know, however, if anybody attempted to extend these results in particular to to the multidimensional case. That might be an interesting thing to look into, actually. Yeah, I hope I answered your question. Any other questions? If that's not the case, I thank you very much for the attention once again, and see you next time.